Hey. Cool. Alright, there we go. For those of you who haven't read the title of the stream, my name is Lewis, and I'm here to talk about simulations and how to use the Python library SimPy to create them. I graduated from UQ last year and was a member of UQCS. While studying, I also worked for a company called Polymathian. They did a talk a few weeks ago about what we do as a company, and if you haven't seen it, I'd go check that out. I've been working for them for about 4 years now, and for the last 2 years I've been working on building up their simulation capabilities. I've simulated a range of heavy industry applications such as underground copper gold mines, barging operations, and vessel movements. And on the right is my UQCS Slack handle and emojis. Feel free to message me if you have any questions after this. Who are you? Hopefully you are interested in learning about simulations. If not, I hope to convince you otherwise. And ideally you're comfortable with Python. At the start it won't matter too much, but as the talk progresses it may get harder to follow along. I encourage you to stick around for as long as you can either way and ask questions because I'll happily answer them. So in the event description I promised an answer to 2 questions. What is a simulation and why do we use them? If you're in a hurry, here they are. You can get on your way. A simulation is a computer program that acts as an approximate replication of a process or system. And we use simulations because they allow us to view how a system behaves and see how it reacts to changes in parameters. Let's have a look at some examples. It's a great example. Here we go. So this is an animation of a simulation that I did at Polymathian. It's showing an underground mine, copper gold mine specifically, and you can see little loaders moving around this underground level, waiting for each other, moving around each other, and it's all updating. The simulations we'll be making today won't look as nice as this, but they'll be built on the same foundations. This simulation helped the client test different operational methodologies, try out electric loaders, different types of equipment, draw ratios, and a whole range of other stuff. Once you've built the simulation, it's very easy to try different things with it. I think move on from that one. Another example is this article by the Washington Post. Some of you would have seen it. If not, that's okay. It's published in March and uses some simple simulations to help explain the complexity of COVID and trying to control it. It uses an approximation of society by having circles bounce around the screen, and when they collide, they can transmit COVID. When this came out, a lot of people still didn't understand what was happening with COVID, and it helped explain how exponential growth happens, what impact certain measures would have, and what flattening the curve even meant. The left image shows it running, and the right image shows a scenario of forced quarantine and what happens when someone escapes. And down the bottom, it's got different methods they tried and what impact that had. This is really useful because it's a fairly complex thing, and even though it's a very crude simulation, it helps explain these topics and you can just instantly see the impact that they have. So going back to these questions, now with the context of those examples, we can see that simulations are very good at educating people on a complex system and doing some what-if scenarios. And as I mentioned, they have different levels of approximation, with the COVID one being far more crude. When you're developing a simulation, you've got to decide how approximate you want to be. Ideally, you want to end up somewhere in the sweet spot. If you go too crude, you don't have enough detail, it's not very useful. And if you go too detailed, you'll end up with detail in the wrong places, you will have wasted time, and you might even be trying to model something that you can't even model in the first place, such as how a human behaves. Typically, when you're developing simulations, you'll start on the left and you'll move your way across, constantly adding little bits of detail and asking what benefit does this provide, and at a certain point it won't provide any benefit for what you're trying to achieve. Now you all came here to see some simulations, to make some simulations, not just talk about them. So let's do that. Here I've got an example that we're going to do. It's a coffee shop simulation. So first we ask ourselves, what detail are we going to model? This one, it's going to be very simple. Customers will walk in and queue up, and a barista will take 5 minutes to make a coffee. I don't know how accurate that is. I haven't timed a barista. And next we're trying to figure out what outcome we want. In this case, given some historical demand, we want to know, is it worth getting a second barista? In this case, this historical demand is actually randomly generated, but it's hypothetically historical. When using simulations, you typically want to use historical data if that's available, because it's far more reliable than you figuring out what you think the system behaves like. Because you're going to be wrong and you're going to miss some nuances, but sometimes that data is not there, and you just have to use what you think is the best representation. So we're going to model this coffee shop very simply. We're going to, at each time step, for this example, every minute, check if a customer arrives, have 3 baristas serve any waiting customers, and decrease the clock until the baristas are free. Now let's put this into some Python code. First, we're going to define how long it takes to make a coffee. As I said earlier, 5 minutes. Next, we're going to define a function called simulate_cafe, which will take a number of baristas and a list of times that customers will arrive. First, we set up the current queue length equal to 0. There's nobody waiting yet. And an array for each barista, an array with an element for each barista saying how long until they're free to make another coffee. We will also store the queue length over time for reporting purposes. So, as I said, we're going to iterate over each time step. I'm doing an 8-hour day, so that's 8 times 60 minutes. Step 1, did anyone arrive? We'll see if the current time step is a time step that somebody arrived at, and if so, increase the queue length. Next, we will go over each barista and check if their current time until free is 0, so they're now ready. And if that's the case, we will serve any new customers and set how long the barista has until they're free again. And then for step 3, we will decrease the time for any barista that is currently making a coffee. We will also record how long the queue length was at this time and return it. Sweet. So let's look at some results. I use MacLeod to plot the results here. On the left is 1 barista and on the right is 2. The x-axis is minutes into the simulation and the y-axis is the current queue length. With only 1 barista, the queue just keeps increasing. It goes a bit up and down and then ends up at 14 people. In reality, people wouldn't wait that long, so you'd lose customers. If we look at the 2 barista scenario, the queue length barely even reaches 2. Well, it doesn't. Let's do some quick calculations to see if this is what we were expecting. It's always good to validate your model against historical data or calculations to ensure that the model is behaving correctly. So we had 100 customers spread evenly over 8 hours, which was 480 minutes of the simulation, which meant that there was an average of 4.8 minutes between customers. And since that's less than the time it takes to make a coffee, we would expect the queue to grow with only 1 barista. Cool. Let's delve into what the simulation is doing from a Gantt chart. It iterates over each time step. Cool. And simulates what happens. Seems fine, right? Well, not exactly. Some of you may notice an issue with this. In this section, nothing's going on. The program is burning CPU cycles, waiting for something to happen. You may think this isn't an issue because there aren't that many of these sections in the simulation. But that's because this simulation is very simple. And if the coffee shop was a lot quieter, there'd be a lot more of these in the simulation. And this problem would get a lot worse. Now let's ask ourselves, is this the only issue with this current methodology of modeling a simulation? Let's have a look at a single event in detail. When a barista makes a coffee, they take a certain amount of time steps to do it. In reality, all the time steps in the middle aren't needed either. We don't care if the barista is halfway through making a coffee. That doesn't affect the simulation. We only care when they start and when they finish. When they start, they reduce the queue length, and when they finish, they can check again to see if there's anyone in the queue and repeat the cycle. Now let's apply this to the original example. As you can see, all the red areas aren't needed. It's not looking too good. In this diagram, there are actually more time steps that we don't need than those that we do. And we bucketed it down to the minute, which might have made sense, but what if we wanted to go down to the second? The previous issue is exacerbated to ridiculous extents. This isn't even down to the second, it's only down to about every 5 seconds because I didn't want to add more lines to the PowerPoint. Just take a second to look how much wasted time is here. 99% of the time steps in a 5-minute coffee are wasted. You might be thinking, knowing this is an issue is cool and all, but what can we do about it? Let's take a look at our current approach. We iterate over each time step. But what if we didn't? To skip over these red sections, we need a paradigm shift. Instead of iterating over each time step, what if we iterated over a queue of times? This would mean that we wouldn't need to iterate over the red sections because they wouldn't be in the queue in the first place. As you can see in the slide, instead of just iterating over each time step, we maintain a queue of times that we want to model, and for each iteration we just pop one off and jump to that time. These two approaches are called fixed time progression and next event time progression. Next event time progression is the benefit of discrete event simulation. When you have a discrete sequence of events that change the system state, you can simply jump to the next one instead of wasting time. Let's have a look at what that would do to our diagram. First, we add in the arrival time since we know we always need to model when a new customer arrives. Next, we start to run the simulation and add new times to the queue as we go, such as when the barista finishes making the coffee. Quick disclaimer, not all simulations lend themselves to next event time progression. For example, physics simulations and the previously shown COVID example need to simulate every time frame. Next event time progression is just another tool you can use, and it is good to know the shortcomings of fixed time progression to properly decide which style you want. Quick shout out to hash.ai. It's an online platform for writing fixed time progression simulations. It's written in Rust and lets you mix and match Python, TypeScript, and Rust components into a single simulation and just plug and play with some really cool animations. Let's see what this next event time progression does to our code. On the left is our old code, and on the right is the new one. There's a bit more going on. Quickly walk through it. At the top, we're importing heap queue, which will allow us to have a heap. If you don't know what that is, it's basically, for this purposes, lets us have a sorted list. We now store when the barista is free instead of how long until they're free. And we now have a time queue which we pop off and push to. So now when we serve new customers, we set the barista when they're free, but we also append that to the time queue, which is initialized with the customer arrival times. Let's have a look at the results. They're identical. After making this code change, the results stayed the same, which is exactly what we wanted. But now we are using the new system. We can change this from minutes to seconds to nanoseconds, and there would be no impact on runtime. That's pretty exciting. However, I must admit, it's a bit tedious. Enter SimPy, the point of this talk. SimPy is a discrete event simulation library for Python. It's designed to make writing simulations with next event time progression easy. Let's write something with it. But first, you'll need to install it, which is just pip install SimPy. Pretty simple. So we're going to write our first SimPy program. On the right is our first SimPy process. Env is a SimPy environment. It controls what time steps the simulation is in, and processes belong to the environment. As you can see in the code, we're using yield, which is a Python keyword for generators, but in this context can be just read as wait for. Very similar to a wait syntax if you're familiar with that. So as you can see, we are taking in the environment, we are yielding or waiting for time out of 10 time units, which don't mean anything unless you provide context to it, and then we print time to wake up. When you run this code, it will just print time to wake up. It only does that. It doesn't need to wait. It doesn't need to actually simulate the 10 time steps that come before it. So now we actually want to run it, and we'll give it a friend called alarm2. Underneath the two processes, we define env to equal simpy.environment, and then we register these two processes with env.process. This just tells the environment that these processes will give it times to add to its queue. And then we run the environment with just env.run. It will just output time to wake up and time to wake up again, because the alarm 1 goes off before alarm 2. Again, it only wakes up for 2 time steps at 10 and 200 because it doesn't need to simulate the rest. And most importantly, SimPy handles all that for us. We don't have that tedious code to check your time queue, appending to it, any of that. It's just a nice, simple API to use. So let's go back to the coffee shop. Let's re-implement it with SimPy. So we define a barista, which takes the environment and loops infinitely, where it will wait for a customer and then it will make the coffee, which is just waiting for 5 minutes. One problem though, how does wait for customer even work? I'd like to introduce you to SimPy resources. SimPy has a construct for resources. Resources have two main functions, a get and a put, one to take from the resource and one to add to the resource. There are various different types of resources for semaphores, homogeneous supply, such as water level, and bag of objects, and you can create your own. Let's see them in action. As you can see, in the barista process, we are using a SimPy resource to model the queue. There is now another process called arrivals. It is in charge of customers showing up and adding them to the queue. Due to these being separate processes, the logic behind them can be separated, while in our previous one they were all together, which is in part because I didn't split them up. They could have been. I personally think this code is a lot nicer than the code we had when we were doing this by hand. I'll let you be the judge though. So as you can see, we're now just doing customer resource.get1 because we only want one customer. And then in the arrivals process, we're iterating through the arrival times, waiting until that arrival time, and then adding that to the queue. We then, as you've seen before, create the SimPy environment. We now create a container, which is a type of resource, and I've put a logging wrapper around it to help with the charting. And then we register these two processes and we run it. And this time we actually give an end time with the until keyword, which means it will stop after that amount of time. Let's see if it worked. Gives the same result, which is exactly what we want. We've now written the same simulation in 3 different ways, and I personally think SimPy is the nicest of those ways. Moving on to a more complex example, or not really more complex, but using different features, is a gas station simulation. So now we're using an object, because they don't need to just be functions. You can use objects to group up your logic. So we've got a car, which takes an environment, a gas station, and a name for itself. It has a refuel function, which just times out for 5 time units, and an action function, which will be the process for it. Where we use Python context managers to request a gas station with the with syntax, and then we yield the result of that. We print out that we've arrived, and then we use yield from, which is again for Python generators, but we can benefit from that in this scenario, where all that will do is basically put refuel in place. So you can just call helper methods that wait for other events. After that, we print that we've refueled, and that's it. Next, we have a process called card generator. It takes an environment and a gas station, and will infinitely loop, waiting a random amount of time to create a car, and then we'll register the car's process to request a gas station and refuel. We then create a SimPy environment and a gas station with 2 units, so this would be 2 refueling stations, and register the car generator process, and we run that for 100 time units. So the really cool thing, 2 cool things about this one are the yield from, which is only available in Python 3, but it just helps splitting out your code a lot more. And this with gas station request. When it leaves this context, when you are no longer in the with, it will automatically release the resource for you, which makes it really easy to control your semaphores. Cool. So, I hope people aren't writing simulations in Python 2 either. I believe with the new version of SimPy, it doesn't even support it. So if there aren't any other questions, the only thing I've got left is writing a SimPy from scratch. The reason I want to do this is because SimPy is really simple at its core, and I think writing it can give a good insight into it and make it seem less scary. It won't be quite as good as actual SimPy, but you should be able to get you should be able to run most of the examples I've shown you. It may get a bit complicated, but I'll try to explain everything as best as I can, but let me know if you aren't following. Okay. Let me pull this up. Okay, so to make SimPy, I've just got a Jupyter Lab here, which will make it easy to write the code. So first we want the SimPy environment. This is what we always needed to instantiate first, and is what the whole simulation is based on. So just quickly make an environment. It doesn't take any arguments as you saw. So we know it needs to know what time it currently is, which we'll represent with now, the same way SimPy does. We also know we want a run function. And there's also the timeout and process functions, which I'll just create quickly. Cool. So this has all the functions we saw that environment had. But it doesn't do much at the moment. At the moment it just has now equal to 0, and that's about it. So we talked about how that time queue works. So we know we need a queue. And we know that for the main loop we want to keep popping from that queue. So I'll go up here. We're using heap queue again for that. And we need to define the queue. Now, this queue will be a list of integers, which will be the time, an event ID, and then an actual event, which we'll define later. This also means we need to keep track of event IDs. The only reason that event IDs exist and that they're in the queue is heap queue requires that you can sort your list. And if you don't define a unique event ID, that sorting will fall over. Because if you have two events at the same time, you won't be able to compare the events and it'll error at you. So now if we go down to the run, we know that we now want to jump to that time. We don't care about the event ID, and we get the current event from popping from the queue. And then we need to do something with that. So before I do that, let's define what an event actually is. It takes one argument, which is the environment. And it has a succeed function, which has a value. Events are very similar to promises in JavaScript, where you wait for them. When you succeed them, they have a value and you can't unsucceed them. So we'll store the value when you succeed. Otherwise, it will be none. Cool. So you wouldn't be able to figure this out unless you experimented with it. So since I know SimPy has this, this is where we're starting to use that knowledge to help create it. But events have callbacks, which is just a list of functions that are called when the event succeeds. But we don't want the event to handle calling the callbacks. We actually want the environment to do that, which is what is done up here. We pass in the event to the callback, which is simply because that's what SimPy does. Cool. So we still don't have a way to actually add things to the environment's queue, which is where a little function called schedule comes in. Schedule will take an event and a delay, which will default to 0, and we'll push it to the queue. So we push with heap queue to now plus delay. We assign the event ID, and then we increment this event ID. So what this will do is when you call it with an event, it'll just push it to the heap with the time being when you want it to be handled, a unique event ID just for sorting purposes, and the event. Cool. Are there any questions yet? If not, I'll move on. So this is pretty much what the environment looks like. It's pretty simple, but it's pretty useless without actual timeouts and processes to use it. So we'll go on to them next. But first, when you succeed in an event, we do actually want the environment to handle it. So we just tell the environment to schedule self. So just when you call succeed on an event, it'll set the value and it will tell the environment, hey, I need to be handled this time step. So our favorite type of event is the timeout. It will take M, like all events, a delay, and let's give it a value, which will just default to true. Question. Seeing that we insert events sequentially into the queue, is there any benefit in using a heap over a simple list? Or am I missing something? You're not missing something. The reason is when you've got two processes. So if I go back to here, you can see that you've got two processes, and they will both push timeout of 10 and timeout of 200 in the same time step, and you can't guarantee which one will come first. If alarm 2 ran first, your list would just be 200, and then the next one would be 10, which would be out of order. And that's the only reason, because they get pushed when the yield happens, which we'll write. And you can't be sure that those will be in order as well. So No worries. Cool. So timeouts are pretty simple. As you see, we've already set the value on the event, which is normally what the succeed function does. The other thing we're going to do is we're also going to tell the environment that we're going to schedule ourselves. So we're not even using the succeed function. And that's what a timeout is. If we go up to here, we can just do that. Cool. But this is still missing a major part of SimPy. We've got the timeouts, the environment, the events, but how do we get the yield syntax? How do we get the nice way of defining these processes in the first place? And how do we even make a process? Because without that, timeout is pretty useless. And this is where it's going to get a bit more funky. Processes themselves are events, so you can yield a process and it will wait until that process is completed. So we'll subclass from event, take an environment, and the other thing we take is a generator. So if we go up here, we'll also fill that in, and then we'll get into how process actually works. So process has a function called resume. It takes an event, and what it will do is it will get the next event from the generator, put that to the queue or deal with it, I should say, because the events do that themselves, and then rinse and repeat. So if we just do this event.value is not none, is checking that the event has actually triggered. We will then so what this is doing is it's calling send on a generator. If you're not familiar with Python generators, this may seem odd. We're sending none, which all that does is pretty much get the next value from the generator. SimPy does some extra stuff with that where you can actually send values back, which is pretty cool, but we're not going to go into that. And we want to catch a stop iteration exception, because when that happens, the process is done, you've reached the end of the function, you don't want to error, you just want to let it finish. So that's how we get the next event. But how do we go from that one to the next one? Well, we don't want to continue on in that process until that has completed. So what we do is we use the callbacks. So now when this event that we've gotten back, for example, the env.timeout5, when that succeeds, which will be in 5 time steps, we'll call this function again with the new event that we get. Oh, sorry, with this event. And then we'll get the next event, process it, so on and so on. So the loop actually happens from these callbacks calling resume. And this is probably the most complicated thing about how SimPy works at its core. And once you get your head around it, it's not that complicated. But we still need to start this loop. So if we just create a simple timeout of 0, because it will happen the same time step. And then we add the self.resume to that callback. So this will just start this loop off with a clean timeout of 0. Cool. I think that should be all we need. Let's try this out. Just create that alarm example again. I'll also add in the time so that we can be sure that it has actually worked. That's about right. Ah, I've got a typo. Also about right, because that doesn't exist. But it works. So, as you can see, we've written SimPy with not much code at all. I could go into writing resources, but I won't. If you're interested in how they're written, feel free to message me. But I won't bore you with that much detail. But hopefully you can see with this how you can build up these simulations and how you can add your own like design constructs like resources, because it's just based around events that you can succeed at your own rate. Yeah, I have only used a single cell. Yeah. I could have split it out, but I just needed something to write my code in. Cool. That's all I have. If anybody's got any questions. If not, then thank you for tuning in.
Alright, thanks so much, Lewis, for the talk. So am I on? Yep. Okay, I'm in frame. Hi. So that's Discrete-Event simulation. So in terms of the event calendar for the rest of the week, we have the competitive programming group as always at 5 p.m. on Wednesdays, followed by the Google Developer Student Club. Our first event, the CLI talk with Hamish. That will be at 6 p.m. And additionally, last week's talk on Finance for Computer Science was postponed to this Friday at 6 p.m. So we have a bunch of events up this week. That's about it. So thanks, everyone. And yes, as you can see here, Lewis was presented with a mug. If you want a mug too, let us know if you want to do a talk, and that can be yours as well. So thanks.